We've seen how to calculate an activation energy for a reaction. We've seen how to calculate the reaction rate constant, lowercase k. We're going to take that lowercase k and we're going to apply it to what's called a rate law. The rate law is a relationship between the rate of a chemical reaction and the concentration of the reactants. A rate law can only be determined by experimental data. You cannot determine any part of this rate law by looking at the balanced chemical equation. So stoichiometry doesn't matter here. What we're looking at is this form here. The rate of a reaction is equal to K, the rate constant, times the concentration of our reactants raised to exponents. Now, in equilibrium and in other reactions, we've used those exponents as the stoichiometric coefficients of our balanced chemical equations. That's not going to be the case here. We can only determine those exponents by experimental data. Now, it's important to note that these exponents will only ever be whole numbers. When we look at this rate law and we look at these exponents will tell us what order the reaction is. When we have an exponent of 1, if we have an exponent of 1, say on the reactant A, then the reaction is said to be first order with respect to A. If there's a 2, the reaction is said to be second order with respect to A. The exponent could also be 0, and then we would say the reaction was 0 order with respect to A. Now, when there's more than one reactant, we will use those exponents to add together to say the overall reaction rate. The overall reaction rate could be 0, it could be 1, it could be 2, and in a rare case, it could be 3. We're going to focus on 0, 1, and 2. Remember, anything raised to the power of 0 is a 1 mathematically, so it effectively gets dropped out of the rate law. So here are some examples. We have the rate is equal to K, the rate constant, times the concentration of hydrogen peroxide. For this reaction, this would said to be first order, both in hydrogen peroxide and overall. In this example, rate is equal to K times the concentration of our reactant squared. That reaction rate is second order with respect to that reactant as well as overall. And here in this example, rate equals K times the concentration of H plus times the concentration of hydroxide. The rate is first order with respect to either of our reactants, but overall this is a second order reaction because we add up those exponents. Remember, the absence of a number is assumed to be 1, not 0. So if we're going to write those reaction orders, those rate laws, and we're given an example like this, we have this chemical equation here, NO2 plus CO reacts to form NO plus CO2. We're going to use our standard rate law expression, and we're going to determine what these exponents will be. I'm going to put little boxes here as placeholders. Remember, only reactants will go in the rate law. The reaction will not be dependent on the formation of products. It is dependent on how the reactants react. So we're told that this is second order in NO2. So that means this second order part is going to affect this exponent, and it will be a 2. It says also in our problem that we are 0 order in CO. So that's going to affect this exponent, and this exponent will be a 0. Again, mathematically, anything raised to a 0 power is equivalent to a 1. So the reaction order, the rate law for this reaction is going to be rate times K the constant times the concentration of NO2 squared, because this part here reduces to 1. Now, I've said that the rate law can only be determined by experimental data. Now we know that the rate is going to be equal to some constant K times the concentration of a reactant raised to a power that we don't know, times our other reactant, again, raised to a power we don't know. So let's look at our reaction data. If we take trials 1 and 2, note trials 1 and 2, the NO concentration is kept constant, but we are doubling the concentration of our ozone. So what happens to our rate here when we double that ozone? If you can't see the relationship, just pop it in a calculator, not a calendar. So I'm going to take my one rate and I'm going to divide it by my other. And it's a doubling as well. So if we double the concentration of ozone, we also double the rate. Because that is a 1-to-1 relationship, this is going to be a 1. This exponent is going to be a 1. Now we can verify that by looking at trials 1 and 3. In trials 1 and 3, again, our NO stays constant, but this time we are tripling the concentration of our reactant. So I would put in the rate of 1, this is the rate of 3, and I'm going to divide it by the rate of 1. And I get 3. So because what happens to the ozone happens to the rate, it's an exponent of 1. Now let's analyze the other reactant. So here we have 3, 4, and 5 that our ozone is going to stay the same. So between 3 and 4, we're going to double the concentration of NO. So what's going to happen to the rate? Well, I'm going to take my rate, 3.96 times 10 to the negative 4, and I'm going to divide it by the rate of 3, 1.98 times 10 to the negative 4. And again, I get a doubling. So because when the concentration changes, the rate changes as well, this should also be a 1. So this reaction is first order with respect to each of our reactants, and overall this is a second order reaction. So now let's complete the reaction rate law by calculating the K. So I'm going to pick any data. I'm just going to pick the first set of data, and I'm going to insert the rate. I'm going to insert what I know, and then I'm going to calculate for what I don't. So in the calculator then, I get a K value of 2.2 times 10 to the negative 7. Now let's briefly analyze the units of that value. We have capital M molarity here and capital M molarity here. For the rate, I have molarity over time, or molarity over seconds. I'm dividing by 2 molarities, so I will have 1 over molarity seconds. To take the mathematical approach to determining the exponents of a rate law, we can use a ratio of the rate of one trial, which is equal to the rate constant K, times each of the reactants raised to their respective exponents, and use a ratio. So rate of 1 to rate of 2, for example. And when something is the same, we can cancel it out. So let's use the rate of 1 and 2. Now typically it would be ratio. So we're going to use 2 to 1. It just makes it easier to see later on. Now because that's going to be equal to K times the concentration of NO raised to an exponent we don't know, times the concentration of Cl2 raised to an exponent we don't know. And that's going to happen for both trials. And the concentration of NO is held constant at 0.10. If 0.10 is raised to the same power on the top and the bottom, they will cancel out, regardless of what that power is. K will also cancel out because it should be the same regardless of the trial. So what we're looking at is the ratio here of the rates, which I can calculate 0.0045 divided by 0.003, and that's going to be 1.5. And that's going to be equal to raised to a power. So the chlorine, and I'm using trial 2 is in the numerator, so that's going to be 0.15. Trial 1 in the denominator is 0.1. So I take that ratio, and that's also going to be 1.5, but it needs to be raised to the power of n. Now I'm going to take the log of both sides. So the log of 1.5 is going to be equal to, and this is an algebraic, well, I would call it a trick, but it's a technique. So the exponent comes forward, and then we're going to take the log of what we were raising to the exponent. Now, to find n by itself, then I would divide both sides by the log of 1.5. So I really don't care what the log of n.5 is, because the log of n of 1.5 divided by the log of 1.5, I keep saying n.5, they cancel each other out. So n is 1. So n is 1 for this reaction rate law. So I will fill it in. So what we're looking for, rate equals, and we'll calculate K, concentration of NO raised to a power, concentration of Cl2 raised to a power. Now this Cl2 we've determined is raised to the first power. So now in order to find the exponent on NO, I will look towards 1 and 3, trials 1 and 3, where the Cl2 is held constant, but NO changes. Now, as before, I want to put the larger rate on top because it just makes my numbers more friendly. And then I will compare. So the rate of NO raised to an exponent that we don't know yet. And I'm just going to fill in the numbers. And then Cl2, I said I was going to fill in the numbers. The Cl2 is going to be raised to the first power. Now, those cancel out. So what we're left with is the rate, the ratio of the rate, 0.00675 divided by 0.003. So that's 2.25 is going to be equal to this ratio, 0.15 divided by 0.1, which is 1.5, but that's going to be raised to the m power. Now I'm going to take the log of both sides, the log log. In the write-up for this example, it says it's taking the natural log. The base 10 log works just the same. So again, the technique, the algebraic technique, even though I seem to be messing up my numbers, is taking the log of a number raised to the exponent will bring the exponent forward, so it's the exponent times the log of that number. So if I divide both sides by the log of 1.5, which I'm just going to do in my calculator, I get an m equals 2. So this exponent here is 2. Now let's derive the value of K. I'm just going to take trial 1 because it seems easy, and I'm going to say that the rate is equal to K, I don't know, times the concentration of NO raised to the second power, because that's what I determined, times the concentration of chlorine raised to the first power. So now I can calculate and find the value of K. And I get that my K value is 3.0. Now let's analyze these units. So the rate is going to be molarity per second. This is squared, so this is molarity squared, and here's another molarity. So that's molarity cubed. So if you have molarity squared divided by, or multiplied by the reciprocal, molarity cubed, then what we're left with is 1 over molarity squared seconds.